So remember what we're doing? We're talking about orthogonal, we're talking about orthonormal bases, right? Orthonormal bases, right? And it turned out that orthonormal bases had some good qualities, right? In particular, they allowed us to get the coefficients for the linear combination that allows you to reconstruct your vector, right? So if you have V an inner product space and U1 through UN an orthonormal basis, then the coordinate vector and then if V is summation Ci Ui, we know that the Ci are just the inner product of V against Ui, right? That was the sort of the big deal about our inner product space, that we could get the coefficients easily, right? Just by taking the dot products. Okay. We're gonna sort of skip back to this in a second. There's a little bit of a digression to something called orthogonal matrices. Orthogonal matrices. Okay, so here's the definition. We say that a square matrix is orthogonal if its column vectors form an orthonormal basis of Rn. In other words, if its columns are orthonormal. Okay. If its columns are orthonormal. To each other, yeah. Maybe say are an orthonormal set. Okay, that's clear. Are an orthonormal set. Right? In that case, they would be a basis because there's n of them, and you'd have n linearly independent vectors in Rn, which would give you a basis. Okay. Okay. So, for example, if we look at the rotation matrix by theta, you remember that looks like this. The rotation matrix, you rotate by theta. This actually is an orthogonal matrix, right? Because the columns are perpendicular to each other, and the magnitude of each column is 1, right? Okay, so this is orthogonal. I always feel like this should be called an orthonormal, right? Why not call it an orthonormal matrix instead of an orthogonal matrix? But the terminology is orthogonal matrix. Yeah, you can.
Explain why that's such an orthogonal matrix.
Well, you just need to see that these guys are perpendicular to each other. These columns. You say, okay, well, let's take the dot product. You get this thing plus this thing. That's 0, right? So their columns are. Here's column 1. Here's column 2, right? Q1 dot Q2 is 0. Q1 dot itself is going to be cosine squared plus sine squared. That's 1, right? So the magnitude of Q1 is 1. The magnitude of Q2 is 1 also, right? So you've got unit vectors that are perpendicular, mutually perpendicular. So that's an orthonormal set. Okay. Properties of orthogonal matrices. first, Q is orthogonal if and only if Q transpose Q equals I equals the identity matrix, right? Right? And the proof of this is you say, well, look, Q is orthogonal if and only if the inner product, the dot product of columns is the Kronecker delta function, right? 1 if I equals j, and 0 if I doesn't equal j, right? That's what orthogonal means, right? That the columns form an orthonormal set. Right? That's what it means to be orthogonal, right? That the columns form an orthonormal set. In other words, when you take the dot product of any two columns, you either get 1 if it's the same column, or you get 0 if they're different columns. Okay? But this is the same thing as saying that QTQ is the identity matrix, because the ijth entry of QTQ is, what's the ijth entry of QTQ? Well, you take the ith row of QT against the jth column of Q, right? But the ith row of Qt is the ith column of Q, right? So you take the ith column of Q against the jth column of Q. Right? So, right? So this thing here is the same thing as saying that QTQ equals I, right? Because this is, this is the ijth entry, right? So the only entries that are 1 are down the diagonal, right? When I equals j, and everything else is 0. Yeah, Brian.
I don't know, can you like draw that maybe?
Yeah. Oh, look. Let's use this one. Okay, so we've got QT, cosine, sine, negative sine, cosine. So we've got cosine, we've got Q, cosine, sine, negative sine, cosine. Okay, let's think about what we get here. What are we going to get? Well, in the 1, 1 entry, we get this thing against this thing, right? That's going to be 1, right? Because the first column against the first column is 1, right? Now the 1, 2 entry, we're going to get this guy against that guy. That's going to be 0 because we're taking the first column against the second column, right? Et cetera, et cetera. Okay, so for this thing to be an orthonormal basis, orthogonal matrix is the same thing as saying that QTQ is the identity matrix. Is that okay? Everybody all right? I said to my previous class, don't worry if you don't understand everything in class. When I was taking math in college, I didn't understand anything in class. I think I understood probably about 10% of what was said in class. But I went home and thought about it a lot, right, for hours and hours, and then I sort of understood it a little bit better. So, yeah, I sort of had sort of a funny, I don't know if we have time for a funny story, but the funny story is that, so that, I don't know if I said this before, but the mathematicians lived in a tower at the edge of campus. And so, if I had a question, I'd go, trudge across campus, to the tower, which was always silent, right? There's the great mathematicians of the world sitting inside, doing their work. And you didn't want to disturb them, right? Because they were sort of like gods. Right? And so I'd have my question, and I wouldn't want to knock on the door. I'd sit outside the door, and I'd think about my question really hard. And then I'd figure out the answer, and I'd go back. So I use this to illustrate the difference between a university and a liberal arts institution. Right? It's sort of like, at least for me, I felt like the professors were very distant creatures. Right? Unlike here, where you sort of pal around more.
Do you wish that you'd like knocked on their door?
Well, I mean, it would have been nice to have actually contact with these people,
Yes.
right? But on the other hand, I felt sort of embarrassed to bother them, right? Because like I knew that they were sort of great people and didn't want to. Okay. Okay, but it would have been kind of cool, right, to get to know these great people. Okay, other properties. Other properties. One, that if you take the dot product, oops, why do I keep on doing that? If you take the dot product of Qx and Qy, it's the same thing as the dot product of x against y. Okay, for all x and y in R. Part two, that if you take the magnitude of a vector and the magnitude of q of that vector, then you get the same thing. Come to think of it, I haven't changed very much. Like last year, I went back for my a couple years back, I went back for the 25th reunion, and there was a professor that I knew sitting in the corner over there, and I really wanted to say hello to him, but I never did. Like it was a math, like gathering of math professors and math major alumni, right? And he was sitting in the corner, a famous guy. I wanted to say hi, but I never said a word to him. Okay. So let's look at this thing, right? That if you take two vectors and then you take q of these guys, then the dot product doesn't change. Okay. So let's prove that. Proof of one, right? The dot product of these things, remember, is qx transpose qy. Right? That's the definition of the dot product. Okay. What's the transpose of qx? X transpose q transpose. Thank you. X transpose q transpose. Right? And so we end up with this. Right? X xt qt q y. Right? But what's qt q? The identity matrix. Right? And so we end up with just x transpose y, which is the inner product, the dot product. Yeah, you do.
Would you be any matrix, or does it have to be orthogonal?
Sorry, these are all orthogonal matrices. So Q an orthogonal matrix. Sorry. Yeah, definitely not true in general. Definitely not true in general. And I should have made the remark here that thus Q is orthogonal is the same thing as saying that Q transpose is its inverse. Q transpose is Q inverse. Okay, part two, right? We want to see that that the magnitude doesn't change when you apply Q to a vector. Okay. Let's prove that the magnitude squared is the same. Because if we show the magnitude squareds are the same, then they are the same, because they're positive numbers, right? So it suffices to prove, it suffices to show that the squares are equal. Right, because these are positive numbers, or non-negative numbers. Okay. Well, why is that true? Why is that true? Why is that true? Look at the first part. Qx, Qy is xy, right? There's a relation. What's the relation?
Because you have to dot qx, or the inner product of qx and qx.
Exactly. This is just Qx, Qx. And by part 1, it's going to be XX, x against x, right? So, by 1, we know that Qx, Qx equals XX. Okay. So that follows immediately, right? This is the magnitude squared. That is the magnitude squared. Okay. So yeah. So the second thing is called Q is an isometry. Q is an isometry. So it preserves magnitudes, preserves lengths. Right? If you have a vector and you hit it with Q, then in fact you just get something of the same size. Okay? And you can see with the rotation that that's clearly true for that rotation. Right? Any vector, you rotate it, still the same size. Okay. Okay. In fact, Q also preserves angles. Q also preserves angles, right? Why? Because the angle between Qx and Qy is cosine inverse of, does anybody remember? Dot product of the vectors. How about you're forbidden to say anything more? The dot product of the vectors over the product of the magnitudes. Right? But by part 1 and part 2, that's the same thing as the cosine inverse of x, y over magnitude of x, magnitude of y. Right? Which is the angle between x and y. Right? So you see that if your matrix has orthonormal rows, orthonormal columns, then it has these interesting geometric properties. Right? It preserves length, it preserves angles. If you hit two vectors with the matrix, then it somehow preserves the angle. Right? It may reverse the orientation, but the angle is preserved. Okay. So that's the end of the digression. Now let's get back to this thing here. Let's get back to talking about orthonormal bases. Okay. I should say that I tried to present this in the first class, and it didn't go over so well. So let's see how it works on you all. Okay, so I'm going to do it in a slightly different order than I did in the first class, since it was so spectacularly unsuccessful. Okay. So Okay, so let me do it like this. Theorem. Okay, so like more properties of orthonormal, more properties of orthonormal bases. Okay, so suppose that V is an inner product space as usual. Let S it be a subspace of V. Okay, and suppose that U1, the UK, is an orthonormal basis of S. Okay, you have an orthonormal basis of S, but you don't have one for all of V. Okay, you've only got part of a basis, right? You've got a basis for the subspace, but not for the whole space. Okay. Then, given any vector B in the big space, if we let P be defined as summation B ui from I equals 1 to k, we have that P minus B is in S per. Further, P minus B is less than or equal to Y minus B for all Y in S with equality if and only if Y equals P. Okay, so let's think about this, right? What does this remind you of? What does this remind you of? It's very similar to something we did quite recently. Least squares, right? This is almost exactly the same setup for least squares, except now we're in an inner product space. Right? With least squares, your V was Rn, your S was Ra, right? The range of A, right? So remember, for least squares, so method of least squares, we had something similar, right? We had some range of A, we have some vector B, and we wanted to find the vector P in the range of A that was closest to B, and it turned out that you needed to find the guy, so you needed P in Ra such that P minus B was perpendicular in the orthogonal complement of Ra, right? Which, by the fundamental subspaces theorem, was the same thing as the null space of A transpose. Right? So that was the method of least squares, right? So we're doing something similar, right? Except, so again, we have some sort of something like this, right? You've got some vector B, right? And you're looking for the P inside S that's closest to B. That's what this is saying. And this is saying that the closest guy is going to be this guy P. Okay. The difference here is that now we know exactly what P is. Okay? We can get P by taking the inner products of B. We take the inner products of B against the orthonormal basis of S, and then use those guys as the coefficients and reconstruct somebody in S. Okay? And that will be our P. Okay? So it's like, it's like we're taking part of the linear combination, right? Over here, we can actually get back our vector, right? But over here, we only have part of an orthonormal basis. We use that part only. We chop it off. We say, well, okay, let's just ignore the rest of it, right? From K onwards, K plus 1 onwards. Okay. So if we ignore, we use the part that we have, we're going to get somebody in S, and that guy turns out to be our projection. Okay. So this is the difference, right? That with an orthonormal basis, we can figure out P easily. Okay. This is the difference, right? We have an immediate expression for P the projection. P the projection of B on S. Okay, we can get it. Okay, is everybody okay? Everybody all right? Okay, so let's show that let's show that this P minus B is actually in S perp. Okay, right, there were two parts. That P minus B in S perp, and that P is the closest guy to B in S. Okay. They say, okay, well, let take any UI, right, in the orthonormal basis of S. Take one of the elements of the orthonormal basis. Take one of the elements in the orthonormal basis, and let's consider P minus B against UI, the inner product. We'll see that this is 0. Okay, that the inner product of anybody in the basis is 0. Well, that means that you're perpendicular to the whole space, right? You're going to be perpendicular. If you're perpendicular to the basis, you're perpendicular to anybody in that space, right? Yeah, Mark.
So this works for like any kind of inner product?
Yeah.
What about even like functions?
Even like functions. So this is the cool thing, right? We're not in Euclidean space anymore, right? We're talking about the Fourier, right? We're talking about the space of continuous functions on negative pi pi. Mm-hmm. Then what's this saying is that if we take a bunch of those coefficients and reconstruct part of the sound, that is actually the closest sound possible. That is actually the closest sound possible to our original sound in the least square sense. Okay, that's the best sound in the least square sense. Okay. Okay, that's why we like it.
Is this from Gauss also?
Is this from Gauss? I don't know, but it's basically the same thing. So even if Gauss didn't do it, he's probably credited for it.
Why is it 0?
We'll see that it's 0 in a second. We're going to do the calculation. It's just a calculation. So calculate. You say, okay, well, P, what was P? P was this guy. We take B against U. Let me use a different index, J, Uj, because I'm using Ui here. It means something else. So J goes from 1 to K, and we use Ui here. Whoops. So this minus B, comma Ui. Okay, let's calculate that. Okay. Take 20 seconds and see if you can see that that equals 0. Yeah, Tara.
I have a question about the Fourier transpose.
Yeah. Fourier
So does that
series, yeah.
mean that higher definition sound means that there's less distance between the original sound and what's being outputted, or is there like no correlation?
Well, okay. So the thing is that no matter how you do it, people are going to chop off at a certain point. Right? You're going to like take say humans can't hear beyond this frequency, humans don't hear below this frequency, and so we're going to chop off at these two ends.
Mm-hmm.
Okay. So adding more will get you closer in the least square sense, but it doesn't improve anything,
Okay.
right? So I can only think that probably it turns out that maybe the least square sense of goodness is not the best sense of goodness for people's actual ears.
Okay.
So it's closer mathematically, but it doesn't sound closer, right? Maybe it's not the best approximation for the human ear.
Okay.
Okay, and so you'd use a different norm. You'd use a different norm, a different distance, and you minimize the distance with respect to this other norm, which is maybe more suitable for human ears.
Okay.
Yeah, that's what I think must be what people do. Okay. Let's do this. What do you get? You see that I got this minus this against that, so I'm going to break it into two parts. Right? I'm going to say this is this first thing against Ui minus the second thing against Ui. Okay, so I just use linearity and I separate this into two parts, right? They're both going against Ui. Now I got like A minus B against C, right? So I take AC minus BC, right? And then I do that on a grander scale, right? I'm going to pull this whole thing out, right? And I get summation constant, and left inside is the vector against this other vector. Right? So I pull the summation and the scalars out by linearity. Right? These are scalars. These are numbers. Right? So I can pull those numbers out. Right? Like if I have summation Ci Ui against Uj, that's the same thing as summation Ci Ui Uj. Right? It's just that my constants are themselves inner products, so it looks more complicated. Okay. As J goes from 1 to K. Okay. But what happens on this left sum here? What happens in this left sum here? As J goes from 1 to K, what happens? Uj Ui is going to be 0, except when J equals I. Let me say it that way, because J is the one that's moving. So J is moving from 1 to K. At some point, it'll hit I, and so when J equals I, we're going to get this will be 1, and we'll get B against Ui. So we get B against UI, line against B against UI. That's 0. Right? So this term on the left just becomes B against UI because everything else vanishes. Right? This is 0 except if J equals I. Okay. So P minus B, that partial linear combination that lies in S is actually the thing that is so that if you look at the difference, then the difference is perpendicular to S. Okay. Let's see that this P is the closest vector in S to B. Okay. The argument is identical. To the previous. We've seen this sort of thing before. You say, okay, well, look, if we take, let Y be in S. If we look at the difference between Y and B squared, that's the same thing as Y minus P plus P minus B squared. Again, P is in S, Y is in S, so this thing is in S. P minus B, we just saw, is in S perp. Right? So by the we have a sum of things that are perpendicular to each other, and we're looking at the magnitude squared. By the Pythagorean theorem, right, c squared equals a squared plus b squared. By the Pythagorean theorem. Right? And again, what you see is that P minus B is less than or equal to Y minus B with equality if and only if Y equals P. Right? Just like we saw before in the least squares method. Right? It's exactly the same argument. Exactly the same argument. Okay. So we can find it, right? So we can find it. Right? We can find the projection just by so the moral is, right, if we have an orthonormal basis of a subspace and we have some vectors sitting outside of that subspace, we can find the closest vector in the subspace by doing this, right? By taking this sort of partial linear combination, right? To reconstruct the part of B that lies in S. Okay, and that will be the projection. Okay. Any questions? Any questions? Still have 5 minutes. We're good. We're good. It worked so far. Okay, now let's get to the part. Now let me tie this back. more closely to the method of least squares. Okay. So let's come back here. Right. So remember, we needed back to the method of least squares. We were looking for the guy in the range of A such that this thing was in the range of A perp, right? Okay, so this guy, remember, was going to be A, what we call AX hat, right? It's in the range of A. It's A of something, right? It's A of something. And so recall, we want X hat solving AX hat minus B was in the null space of AT, right? That was the normal equation, right? That was the normal equation. Okay, in other words, ATAX hat equals ATB. Okay, and remember, A was a m by n matrix, where m was bigger than n. Okay, so now let's think. Now, suppose that A is orthogonal. Well, actually, maybe I shouldn't say that because it's not square. So let me say, suppose A has orthonormal columns. In other words, the columns are an orthonormal basis of the range of A. In that case, so A was an n by n matrix, right? In that case, ATA is still the identity matrix. Right? It's an n by n identity matrix. Right? So the normal equations become this. X hat equals A transpose B. Right? Because the normal equations, remember, are this. Right? ATA X hat equals A transpose B. Right? But ATA, right, if it's got orthonormal columns, then ATA is going to be that. Okay. But then P is AX, which is ATB. Okay, right, so this is the projection. The projection of B onto the range of A. Okay, so you notice two things. One, that AAT projects a vector, any vector, onto the range of A. Right? If I take any vector, I see that A transpose B is the projection. Notice that A transpose is not the identity. Okay. By the way, A transpose is not necessarily the identity. This is because it's not square matrix. If it were square matrix, yeah, it would be the identity. Okay. Part 2. What is AAT? What is AAT of B? What is the projection? Actually, you know the answer already, but let's spell it out. Okay, let's think. A looks like this. Column 1, column 2, column 3, column n. Right? A transpose is you take A1 transpose, take that column and transpose it, take the columns and transpose them. Right? And then we have our B over here. Okay. A transpose B equals this. Right? So this was m by n, this is n by m, this is m by 1. Right? From this, I'm just going to multiply the latter two. Let me multiply the latter two here and keep the first. This is A1 through AN times, it's going to be now n by 1. It's going to be n by 1 matrix. M by n, n by 1. Where the entries are the inner product of A1 against B, the inner product of A2 against B, inner product of AN against B. Sorry, the dot product, right, because we're in Rn. Right? But what's this? If you take a matrix and multiply it by a vector, what do you get? In terms of the columns, you've got a bunch of coefficients, you've got a bunch of columns. What do you get? The linear combination of the columns with these as the coefficients, right? You get the linear combination of these guys against the columns. Right? Which you've seen before. This is exactly what we said theoretically before, right? That the projection, right? This is the projection. This is P, right? The projection of B on the range of A, right? Which has orthonormal basis A1 through AN. Right. This is the closest vector in range of A to B. But that's what we said before with all this theoretical stuff, right? That the guy who's going to be the closest, is this guy, P, right? You take summation from j equals 1 to k of B against the orthogonal basis, and reconstruct using that orthogonal basis, right? So this just goes to show you that it all is in accord, right? It all works out as it should, right? I mean, in some sense, we didn't need to do this again, right? Because we knew it theoretically. Okay, but you see that if you're if your basis, if your matrix has orthonormal columns, you indeed get what we thought we were going to get, what you're supposed to get. Okay, that's it. That's it.